Okay, so in this video, we're going to talk about kinetic energy and the work-energy theorem. Before we do that, I want to take a look at this question. And you had a similar question posed on your worksheet. But basically, this question says, a particle of mass m is moving with constant speed v in uniform circular motion. What is the total work done by the centripetal force during one revolution? Okay, and of course it would help if you knew, that the centripetal force, provided the situation shown is from gravity because it shows the moon going around the Earth. But it actually doesn't really matter the context of the situation because the work done in the situation, regardless of the actual situation itself, is zero. Okay, and it's not because of the word one revolution. This is actually a misnomer. It has nothing to do with that. Some people might think, well, okay, so in one revolution, it ends it back where it starts, and so the displacement is zero, which is true. But even if you took out the word one revolution, the work done would still be zero. And the reason is, when you're talking about uniform circular motion, the motion of the object itself is tangential. Right, we talked about tangential velocity or linear velocity in the last unit, whereas the centripetal force, regardless of whether it's from gravity or tension or normal force or friction or whatever situation, is always radial because it always is radially inward because that's what centripetal means, it's center seeking. And so if you imagine drawing those as vectors like this, okay, the displacement is going to be in the same direction as the velocity, that is tangential. The force, the centripetal force, is always going to be towards the center, and the tangential direction and the radial direction are always perpendicular. And we learned in the last video that if the force and displacement are perpendicular to each other, that is, if theta is 90 degrees, cosine of 90 degrees is 0. In other words, that force does no work. Okay, and so regardless of the actual situation itself, the work done here is 0 joules. Now, if you want another more conceptual way to think of this, you can imagine that work is the transfer of energy to or from an object. And so, um, in this situation, if it's uniform circular motion, that means the object is going in a circle, but it's not actually moving any faster or slower. Okay, meaning that it's not gaining or losing energy, meaning that there's no net work being done to the object. Right? Because if there was energy being added, it would be spinning faster, and if energy was being removed, it would be going slower. And so if it's in uniform circular motion, it's not going faster or slower, which means that the net work done on the object has to be 0. Okay, and so whether you think of it mathematically or conceptually, you still get the same answer. Okay, and so hopefully that answers the question that many people had about that worksheet question. All right, so with that out of the way, let's move on. Just to recap, in the last unit we talked about, or not the last unit, the last video, we talked about work, both conceptually and calculation-wise. The concept of work is the transfer of energy via force to or from an object. Okay, so when you talk about work being done on an object, you're talking about a force, a specific force, either adding or removing energy from an object. Okay, and of course, in the situation where you have a constant force, the work done by that force is given by the equation Fs cosine theta. Now, if you don't have a constant force, that's actually where calculus comes in, but we're not going to be doing any calculus-based problems. But this equation would not work if the force itself was not constant. We also talked about the idea of network, which is basically what you get when you find the work done by all of the forces on an object and that add up each individual piece of work. Okay, so kind of like net force is the sum of the forces, net work is the sum of the works done by all those forces. And what you're doing there is you're adding scalars, not vectors. And so calculating net work is not difficult as long as you understand how to find the work done by each individual force. Okay, so that's just a quick recap. Now, in this video, we'll learn like why did we, talk about net force to begin with. Okay, before we get to that, let's introduce our first type of energy. Because work is not a type of energy, it's just a mechanism for transferring energy to or from an object. Okay, so let's talk about our first type of energy in this unit, which is going to be kinetic energy. Okay, so let's add this to our notes. So kinetic energy as the name would suggest, is the energy of motion. Okay, that's what kinetic means. Okay, so very simply, if an object is moving, it has kinetic energy. And if it's not moving, then it doesn't have kinetic energy. But I guess we can be a little bit more specific than that. We can calculate the kinetic energy, which I will do EK for kinetic energy, using this equation. Okay, so the kinetic energy of an object is equal to 1/2 times the mass of the object in kilograms times the speed of the object squared. Okay, so 1/2 mv squared, 1/2 times the mass of the object times the speed squared. And so you can see from the equation that if the speed is 0, if it's not moving, the kinetic energy is 0. Okay, so make sure you have that equation down. We'll just do a really basic calculation with that really quickly. Okay, so example 1 says a ball with a mass of 6 kilograms falls and at one moment in time has a kinetic energy of 300 joules. How fast is the ball moving at this moment in time? So this is just like a really baby type of calculation to do. How fast is obviously a question about speed. And so if we have the equation 1/2 mv squared, we know at one moment in time it has 300 joules of kinetic energy. That's equal to 1/2 times the mass, which is 6 kilograms, v squared. And so all I have to do is do a little basic math here and get v by itself. Okay, and so if you 300 divided by 3 is 100, and so v would be 10 meters per second. Okay, so that is the answer to example 1. Okay, so just a really baby type of calculation, just getting us used to seeing and using the equation for kinetic energy. Okay, so pause there, make sure you have that in your notes. Okay, so let's do another one or two little baby calculations with kinetic energy, and we'll go back to the work energy theorem. Okay, so example 1.5 says an object with mass m and speed v has kinetic energy Ek. State in terms of Ek the kinetic energy of an object with mass 2m and speed 2v. Okay, so we've seen this type of problem before. This is our good old friend proportional reasoning problem. So I want you to try to do example 1.5 on your own using the equation for kinetic energy. Okay, so Ek equals 1/2 mv squared. See if you can answer this question. Remember that your answer should be a multiple of Ek. Okay, so your answer should be some number times Ek. So try to answer that now. Okay, so originally we have Ek equals 1/2 mv squared, and we're basically asked how does the kinetic energy change if the mass doubles and the speed also doubles. And of course we could imagine, yeah, the kinetic energy is going to get bigger, but by how much? Okay, so let's take a look at this problem. We basically want to find Ek prime and make the substitutions they tell us to make. So 1/2 times the mass, but now the mass is 2m, times the speed squared. So now instead of doing v squared, I'm going to do 2 times v and then square that. Okay, so 2 squared is 4. 4 times 2 is 8, and then half of that is 4. And remember that my objective is to find Ek prime equals some number times Ek. And so one way I can do that is just to divide by my original Ek, which is 1/2 mv squared. And what I end up with is 4 divided by 1/2, which is 8. So in other words, the answer is 8 Ek. So doubling the mass is going to double the kinetic energy. Doubling the speed is going to quadruple the kinetic energy. And so when you combine doubling and quadrupling, you get multiplied by 8. Okay, so that is the answer to example 1.5. Pause it there if you need to look at that some more. Okay, and let's just do one more quick example with kinetic energy. So example 2, state the units of kinetic energy in terms of fundamental units. As we're doing these problems, by the way, do keep in mind I'm always like trying to prepare you for problems that you might see in the future. I'm not trying to give you a hint or anything, but I'm telling you that one of the skills that the IB expects you to be able to do is to write the units of something in terms of fundamental SI units. And so this is not something that we've done before, so this is going to be kind of a new skill, but I want you to see how this works. Generally speaking, if we want to find the units of something, what we have to do is we have to take an equation that has that something in it and plug in um, plug in units into the equation. Now, for example, I know that work is Fs cosine theta, and I know that work is measured in joules. Okay, and so what I could do is I could say, okay, so work, force is in newtons, and displacement is in meters, and cosine theta has no units. So what I could say is 1 joule is 1 newton meter. The issue with that is that doesn't answer this question because newton meter is not fundamental. Okay, meter is fundamental, but newton is not because newton is a derived unit. All right, so I can answer this question using my kinetic energy equation because kinetic energy is also in joules. And so what I can do is I can take this equation. I know EK is in joules, and I can plug units in to the right side. Okay, so 1/2 times the unit for mass is kilogram. Speed squared would be meters per second squared. And the 1/2 doesn't really change anything about the unit at all, so I don't really care about the 1/2. But what I find is 1 joule is equal to 1 kilogram meters squared per second squared, or in IB notation, 1 kilogram meters squared per second squared. This is the answer to the question because this is written completely in terms of fundamental SI units, okay, as opposed to Newton meter, which is the exact same thing except it's not written in terms of fundamental units. Okay, so my point is you can find the unit of something by taking an equation and plugging units into that equation, which we've kind of seen before in the past. This is just like another extension of that. Okay, so enough about the basics. Let's get to a more substantial theorem. So we just talked about kinetic energy, the kinetic energy equation, 1/2 mv squared. We'll spend, lots of different problems using kinetic energy in the future, so that's an equation that you should know. But what we're going to talk about now is one of the key concepts in this unit, and that key concept is called the work-energy theorem. Okay, the work-energy theorem. Here is what the work-energy theorem states, and I put it in bold so you can add it to your notes. The work-energy theorem states that the net work done on an object is equal to its change in kinetic energy. So let's see, how can we write this mathematically? So the net work, so W net, the net work on an object is equal to its change in, it's always delta, and kinetic energy is EK. This right here is the work energy theorem, and this is how I would give it to you on an equation sheet. W net equals delta EK. Now this form doesn't really help you, so you also have to understand how to expand this equation out. Now what do I mean by expand it out? Well, here's what I mean. Anytime you have change in, you always write that delta in math. Change in anything is always final minus initial. So I could rewrite the work energy theorem by expanding it out a little bit. Instead of writing delta EK, I could write EK final minus EK initial. Okay, so I've kind of expanded out the delta. Now, this form of the work energy theorem may or may not be super helpful. I might need to expand it out one step further. Now, what I mean is, I know kinetic energy is 1/2 mv squared, and so if I had to, I could use that fact to expand the work energy theorem out one step further. In other words, instead of writing EK final, I could write 1/2 mv final squared. Okay, so instead of EKF, I'm plugging in the equation for kinetic energy in its place, minus 1/2 mv initial squared. Okay, so this is what I would give you. Wow, I can't even draw a straight line. That's embarrassing. So this is all I would give you on your equations on the test, but the other two forms might be more helpful in actually solving problems. Okay, so pause it here. Make sure you have this added to your notes. This is one of the key concepts in this unit. That's the work energy theorem. And I do want to point out, by the way, that we've already talked about what net work means. Okay, in fact, we just took a quiz over that recently. All right, so basically this is saying if you add up all the work done on an object, all the energy going in, all the energy going out, the overall result changes the kinetic energy of the object. And that's what the work energy theorem says. Okay, so now we're just going to do a couple examples with this concept before we finish out this video. Okay, so we're going to start with a very basic calculation with example 1. All right, so example 1 says, as a 20 kilogram shopping cart with 500 joules of kinetic energy rolls down the aisle, the force of friction acting on the cart does negative 200 joules of work. Calculate the new kinetic energy and speed of the cart. Okay, so what I want you to do is try to answer that first question on your own, very basic question. Calculate the new kinetic energy of the cart after the force of friction does negative 200 joules of work. Okay, so try to do that now. All right, so there's two ways to approach this question. This is a work energy theorem question. Net work is equal to the change in kinetic energy. That form doesn't help us at all, so we're going to start to try to expand it out at least one layer. So I have EK final minus EK initial. Now, we have the mass of the shopping cart, that's good, and it says it has 500 joules of kinetic energy, and then, as it rolls down the aisle, the force of friction does negative 200 joules of work. Now, if you imagine the forces acting on the cart, we've got gravity and the normal force, and neither of those two forces do any work because they're both perpendicular to the direction of motion. So there's three forces acting on the shopping cart as it slides, but the only one doing any work is friction. Okay, so friction does negative 200 joules of work. That means the net work on the shopping cart would be like 0 plus 0 plus negative 200, which is just negative 200. We're asked to find the new kinetic energy, that is EK final, and we're given the initial kinetic energy is 500 joules. So if we add 500 to both sides, we get 300 joules of kinetic energy. And that's the answer to the first question. Hopefully you got that. Now, you can answer this really quickly if you understand the concept. Remember, concepts are always important in physics because remember, work is the transfer of energy to or from an object. And so when we say negative 200 joules of work is done, that's the same thing as saying that friction takes away 200 joules of energy from the shopping cart. So if it has 500 joules to begin with and you take 200 joules away, that gives you 300 joules, which is what we got as the answer. Okay, so if we want the new speed of the cart, now we have to actually bust out the kinetic energy equation because its kinetic energy is 1/2 mv squared. So the final kinetic energy would be 1/2 mv final squared. And so now that I know EK final is 300, I can plug in 1/2, the mass is 20, I'm looking for V final squared, and I just do a little algebra to answer the question. So that would be 30 equals VF squared. Then I'm going to take the square root besides square root of 30 is 5.5 meters per second. Yes, that is the answer to example 1. Pause there if you need to look at that some more. Alrighty, so moving on. Okay, so example 2 says, a cat of mass 12 kilograms is at rest. Right off the bat, I got mass, I see it's at rest, and the question says how much work is needed to accelerate the cat to 5.5 meters per second. Okay, so pause here, try to answer this question on your own. Okay, so this is a very easy question. People will get messed up by this word accelerate. They're like, oh my gosh, acceleration, what is it talking about? All that means is the velocity is changing. I mean, it's changing from 0, which was the initial velocity, to 5.5 meters per second, which is the final. Or I keep saying velocity, I should be saying speed. Really, it's speed. Okay, so V final is 5.5 meters per second. Now, I want the work done to cause this to happen. And I know from the work energy theorem that's equal to the change in kinetic energy. Now I need to expand this out to a more useful form so that I can actually find the work done. And so I'm going to expand it all the way out to 1/2 mv final squared minus 1/2 mv initial squared. I do that because of what I'm given. I'm given 2 speeds, so I need to expand it all the way out to the form that has speed in it. So the net work done on the cat would be equal to 1/2 times the mass times 5.5 squared minus the initial kinetic energy, which is 0 because the cat is initially at rest. Okay, so in my calculator, I'm just doing 5.5 squared times 12 times 1/2. That's going to be, let's see, 181.5 joules, and that's the answer to this question. Okay, so pause there if you need to look at that some more. Okay, let's take a look at example 3. So example 3, we get this little mousetrap car here that some of you might have built when you were younger. It says a 0.4 kilogram, there's a space there. 0.4 kilogram mousetrap car uses energy from a spring to move. Assuming that the car is initially moving at 0.1 meters per second, calculate the kinetic energy and speed of the car if the spring does 1.5 joules of work. Okay, so the spring does 1.5 joules of work, meaning it's adding that much energy to the car. Okay, and the car already starts with some initial kinetic energy, and so this is going to be a work energy theorem problem. So I start with the work energy theorem. That's equal to change in kinetic energy. Now I'm going to need to expand this out a little bit, but I want to find the new kinetic energy and the new speed, and so I'm going to start by just expanding out to the first layer. So that's going to be EK final minus EK initial. Now the problem with this form is I'm looking for EK final. I'm given the work is 1.5. I want EK final, but the problem is I don't have EK initial. However, I can calculate EK initial because that would just be 1/2 mvi squared, and I have all of the values to do that. Okay, so I've got the mass, I've got VI, which is 0.1 meters per second. So I'm going to my calculator, I'm going to do 0.1 squared times 0.4 times 0.5, and I get, wow, 0.002 joules. Should be a decimal there. Okay, so that's how fast, or that's how much kinetic energy the mousetrap car initially has. So that is my EKI, which means that EKF is going to be 1.5, let's see, 1.502 joules. All right, so that answers the first question to calculate the kinetic energy of the car, but now I want to know the speed of the car after the spring does work, which basically means I want to find VF. All right, so from here, I can go back to my equation for kinetic energy. Kinetic energy EKF equals 1/2 mvf squared. And so I have 1.502 equals 1/2 times 0.4 times VF squared. And then I just need to do a little bit of algebra. And I'm going to skip some of those steps because I don't feel like writing them down. But hopefully you can do basic algebra and arrive at the correct answer. And you should get VF is about 2.7 meters per second. Okay, so the spring inside the mousetrap actually adds a lot of energy to the toy car and makes it go much, much faster. Because initially it was going 0.1 meters per second, now it's going 2.7 meters per second. Okay, so pause there. I think that is going to be the last example we're going to do with the work energy theorem. The only types of problems that we did not see that we might take a look at later on, or you might see on your practice worksheet, are problems where you have to calculate the net work using methods we talked about in the last video, where you find basically you have to use a work equation um, to find the work done by each individual force, and then add all those up, and then set that equal to W net, and then use the work energy theorem. And so a lot of the times when you're doing problems with the work energy theorem, you have to use it like in combination with what we talked about in the last video with work and network. All right, but besides that, you should have a good understanding of, what is kinetic energy, what does the work energy theorem say, how do you solve different problems with the work energy theorem, and hopefully you should be able to use your new knowledge to start working on your work energy theorem practice worksheet. Alrighty, so as always, please let me know if you have any questions, and I'll see you guys in the next video.